Hey kids, so here is what we did the other day. We're gonna stop. I was just reading what I had to do next. All right, we are going to start with revisions to what Dalton thought. So remember, Dalton back in the 18 whatevers did some wrote down everything that was known about atoms and it's Dalton's theory, and these are some of the things that changed. And we teach you history because things change. And so this is our understanding of the atom now, understanding meaning that in 200 years we may have made some discovery that means we need to update this understanding. So this is how we understand the atom right now. It is not by any stretch locked in stone how this will be for the rest of your life. All right, so he thought atoms contain, he thought atoms were indivisible, that you couldn't divide an atom any further. That is not true. It's actually we discovered protons and neutrons and electrons, and we call these subatomic particles. So we can actually get a proton and a neutron and electron to show up at, when we need one every now and again. So therefore, we can divide an atom further. We also discussed how an atom is mostly empty space, that the nucleus is a very small part, dense part of the atom. That's what Rutherford did when he was shooting his alpha particles at the atoms. They were bouncing back occasionally, and if we had a nucleus the size of a grape and we put it at the center of the RBC center, the electrons would be running around as far as the upper deck of the stadium. So if you think about the only thing you would get bounced back from in an atom would be the grape, and you were shooting stuff through the RBC center, that would be like alpha particles. That's an example or a model of how much empty space there is. And electrons do not fly in an orbit like this picture has. They're actually more random. They're like preschoolers running around, but they are probably in certain areas. There's probabilities that Heisenberg and Schrodinger figured out. And that is just mathematically, they could figure out areas where they would be and areas where they wouldn't. All right, so here are the subatomic particles. There are electrons, symboled with an E with a negative sign. That negative sign relates to the fact that the relative charge of an electron is -1. We say it has a mass number of 0. That doesn't mean it has no mass. Its actual kilogram mass is over here. But it's so small compared to everything else in the atom that we say relatively it doesn't have a mass. And we talked about how that would be if Mr. Roach were to eat one M&M, his mass would not go up, right? If I got on the scale before and after eating an M&M, the scale would not show me any difference. And that's true with an atom as well. Atom's mass is all in the protons and neutrons. And when you add an electron to that, it's not going to be significant enough to knock that atom up any on the scale. So protons, P plus symbol because they have a positive charge, and proton starts with P, have a +1 charge and a mass number of 1. Neutron has no charge, neutral, right? Hopefully, so that's symbolized by N0. Also has a mass number of 1. So we talked about the charge is right here, and the mass is right here. That's how an electron works, or an atom works. And that we use atomic mass units because kilogram wise, we were going to have these huge numbers, or gram wise, just not huge numbers, but a number with so many zeros in it that we wanted to use something quick and easier. So we just defined an atomic mass unit as that many kilograms. All right. You all did really well in that quiz. So remember, electrons have insignificant mass and they don't fall into the nucleus because they're moving around so quickly. We talked about the electrons are attracted to the protons. We all got magnets in our hands and we showed how magnets are attracted when they're plus minus and they're repelled when they're either plus plus or minus minus. So that's sort of the way the electrons and protons work. Electrons repel each other, protons repel each other, but protons and electrons attract each other. Okay. So some definitions. The atomic number is the number of protons in an element, and this is what defines the element. So if you are looking at a periodic table, I think I have here now, right? all these numbers here are the number of protons. And as you can see, they go up in sequential order because once you change the protons by one, you change the element and you have a new element. So we also played this game here on PhET, right? Where every time you add a proton, right now I'm at carbon because I have 6 protons, but if I had a 7th proton, I'm at nitrogen. If I had an 8th proton, I'm at oxygen. So we talked about how the number of protons is what changes, right? I can add a neutron here, doesn't change the element. I can add an electron here, doesn't change the element. The thing that changes the element is adding or subtracting a proton. Okay, so back to what I was talking about. So that's why we call the atomic number the number of protons. That's the one that defines the element. The mass number is just the sum of protons and neutrons. I'm not going to go nuts with these symbols because they don't make sense in English. They were probably invented by some country where Z and A make sense. So don't worry about that. The ionic charge is due to the electrons being gained or lost. So if you need to make carbon positive, why do I keep doing this, you wonder? Because I can, kids. All right. If I need to make carbon positive, the way to do that is to take away an electron, not to add a proton, because if I add a positive proton, I turn carbon into nitrogen. I no longer have positive carbon. So we do not add protons. We take or add electrons to make either a positive ion or a negative ion. Okay? So we don't mess with the protons when we're trying to make ions. We only mess with electrons. And if you think about it, if I go back here, since electrons, even though I just told you this is a bad model, since electrons are on the outside of the atom, it's easier to access, add, and subtract them than the nucleus, which is way in the middle of the RBC center. It's easier to just go in the upper deck and take an electron away in the RBC center. All right, getting back to this. So we adjust electrons to make the charge happen. And you all did really well in this quiz, so I'm not worried about that. All right, so here is how it is written in nuclear notation. You put the symbol from the periodic table, and you have a superscript that is the mass, and you have a subscript that is the atomic number. And I told you, if you ever wonder which one goes where, just look around whatever test you're taking. It's not even just mine. Any test will have this somewhere if it's testing you in chemistry. And you'll see the bigger numbers on the top and the smaller numbers on the bottom. And that will remind you, oh yeah, the protons go down here and the mass goes up there. All right. I don't know why I'm not. Oh, so this is for one atom. That's what that's all about. This is for, it's like, why aren't I moving forward? This isn't for all the atoms. This is for one atom because many of you smarties said, well, wait, this number says, 12.001. How can carbon have a 13? We're talking about one atom of carbon which has 13 electrons or 13 neutrons. So let's just start here. Let's talk about sodium. So sodium, Na, right there, has how many protons? That has 11 protons. Its nuclear notation is Na. So we're going to put an Na here. Because it has 11 protons, and because protons and neutrons make up the mass number, right? These two things make up the mass number. We can tell that 23 minus 11 will give us this. So that is 12. All right. 23 minus 11 is 12. And so that's telling us how many neutrons there are. All right. Electrons, I will change to yellow. Electrons and protons contribute to the charge. Since the charge here is +1, that means that the sodium protons, there's one more proton than electron. So that would mean there are 10 electrons. And if you think about it, what I told you to think about it was if we have 10 electrons, let's put it here 1, 2, 3, 4, 5, 6, 7. You're not going to see it in there. 8, 9, 10, 11. You are going to see it there. Oops, 10. 10. I'm going to need to erase one. Let's erase one. All right. And then let's do protons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So when we have this party with protons and electrons, there is one proton left with no electron to accompany it. So that's why the charge is +1. It's a +1 charge because there's one positive by itself. All right, arsenic, As76. If we go to this, arsenic is, I said arsenic, so therefore it's here. So this is one where you'd say, well, wait, Mr. Roach, the mass is 74, 75. How could there be 76? We're talking about one atom of arsenic, not all the arsenic. This here is talking about all the arsenic, which we'll talk about in the next video. But let's get back to this arsenic. So we just figured out that's arsenic. And the number of protons, it's telling you here, this information is trying to tell you stuff. And would the smaller number be the mass or the protons? Hopefully you realize the smaller number is the protons because the mass is the bigger number because it's the combination of protons and neutrons. So if that's 33 for the protons and then mass is 76, that would make this have to be the neutrons, the difference between the protons and neutrons, which is 44. So that's 76 minus 33. Oops. And then for the electrons, since there's no charge here, and the electrons contribute to the charge with the protons, and there's 33 protons, that means there has to be 33 electrons. All right, hopefully that makes sense. We are going to discard all that, and I will now make a video for you if you want to know about isotopes.